In a common Chem 1 lab, what we'll do is we'll take some metal, usually steel or something, and we'll put some acid around it. The acid is going to start reacting with the metal. It's going to steal away electrons from the metal, causing the metal to dissolve. In the process, we're going to be liberating hydrogen gas. The H pluses are stealing 2 electrons to make a bond, and they're popping out as H2 gas. Now, obviously, if we have gases forming in a liquid, we're going to see them bubbling to the surface and eventually creating a headspace of gas over top, right? Well, how are we going to account for the fact there's also going to be some humidity in there when we're trying to make a measurement and determine how much gas we've actually generated? Luckily, there's a law for that, Dalton's law of partial pressures. Now, what Dalton's law realizes is that the total pressure is going to be based off the pressure of each of the gases that are present. So, since they're not interacting, we can allot the total pressure back to each of those gases based on how much there is present for each of them. Now let's see what that means in practice. Suppose that we're bubbling hydrogen gas through water. We have some unknown pressure of dry H2 that we're going to use in the ideal gas law to figure out how many moles of hydrogen gas we just made. There's also going to be some evaporated water, and let's say that we're at close to room temperature where we'd have about 20 torr of water vapor in any gas. Our humidified H2 gas is going to equal our ambient pressure in the lab, unless we do something special to actually make it an elevated pressure, but generally we wouldn't do that. So we're going to be at about 780 torr of humidified hydrogen gas. So we can work that backward to determine how many torr of dry hydrogen we've got. Well, 780 total, 20 of it was water, so 760 torr must be of dry hydrogen gas, if it had been dry. So, here we are, H2. That's how we use Dalton's law of partial pressures to find out what contribution each of those gases made. Now, also, let's generalize it now. The total pressure is going to equal the total of each of the partial pressures. In other words, the pressure of each of the gases that have been mixed in. Now, we also know that we could set up an ideal gas law for each and every one of those, where we rearranged it so that it's P, V equals nRT. We'd cancel out the volume, and we put it on the other side. Pressure equals number of moles times ideal gas constant times the temperature divided by the volume. You can see that we've plugged that in for each of those individual components right here. Now notice we have a subscript on the number of moles, but on nothing else. Well, there's a reason for that. R? Well, notice R is a constant. It's not going to change depending on which gas we're talking about. The gases are mixed together. They're going to be at a uniform temperature. They're also not going to matter which gas we're talking about. It's all going to be a uniform temperature. We're going to use it, but we don't have to have it specified for each of the gases. They're also going to be sharing the same volume. So volume doesn't have to have an index number to it either. It's not going to be dependent on which of the gases we're talking about. So when we chain them all together, we get total pressure equals number of moles times RT over V, which means we can also simplify this by just taking RT over V, pulling that out front, and putting everything else in parentheses where we just say N1, N2, N3. So it would be equals N1 plus N2 plus N3, and on and on and on, times the RT over volume. You can see that these are the exact same things that we've just said. So we can specify each and every one of those, or we can just say the total number of moles is all that matters. That's the same idea. Now the other thing we can do here is we can take the percentage of moles that are present, and that'll dictate its contribution to the pressure. So if you know the mole fraction, that's the term for that, then you'll know the partial pressure of that gas. Now mole fraction is given as capital X, or more often capital Chi, which you'll see is kind of like a handwritten cursive looking X. The mole fraction of that particular molecule is going to be the molecule's number of moles divided by the total. In other words, this is the percentage just without the times 100%. So it's just without that piece of a percentage calculation. And we can lay it out just like that. We can say the pressure of each gas is going to be its mole fraction times the total pressure. So notice up here, I can also figure out the mole fraction working backward. If I've got water, and the water was 20 torr, the total pressure is 780 torr, then from that alone I can determine the mole fraction. I would just grab my calculator and type in 20 divided by 780. So my mole fraction of hydrogen gas of water vapor in the hydrogen gas is going to be about 0.0256. And of course, the sig figs are ambiguous here, so I'll just kind of leave it at that. I'll just write it as 0.025, actually 0.026 with rounding, 0.026. That'd be the mole fraction for water in this case. And of course, the rest of that 100% would be from the hydrogen. So it would be, well, I could either just go ahead and calculate it again, or I could just subtract that from the value 1. And either way, I'd get the partial pressure of the dry hydrogen mixed in to make the humidified hydrogen.